This is joint work with Theo Bergelia, who's in Laboratory of Thermokinetics in CNRS in Nantes, on the Atlantic coast. It's a really beautiful town. Probably went to sleep as John entered. That's good. And Miguel Moyers Gonzalez, he's a non-Newtonian fluid dynamicist in my school. So we just have two sections. I'll just give a little bit of motivation for so-called yield stress or viscoplastic materials. Then we'll just get into the model. We'll do a microscopic, mechanistic, interacting particle system model. That's what we'll do. The background will be very brief on phenomenological models that petroleum engineers who have their feet in the fire are using to make sure oil keeps flowing out of the wells. Because if oil's rate, shear rate reduces, it'll get stuck. And then we can't try and get our kids. Okay, it's a big problem. And I don't know what the engineers do. They really have their feet in the fire. This is just, and if somebody knows something that I'm doing stupid, please let me know, because I can't find physicists that are into this in the little island I live in. So what are these viscoplastic fluids, and why should we study them? Well, if you're into eating sweet things, it's very important to understand the rheology, the flow of chocolate, for example. Because you need to control it at the right rate, maybe not put too much heat on all sorts of things. So, while of course lava is another rheological viscoplastic fluid. Of course, they all have their characteristic temperatures and timescales, and the stress you need to turn them from a solid to a liquid, and vice versa. That's the oil well I was talking about. Salute the commander-in-chief who ensured that oil will flow out of certain parts of the planet, which is good in his address. And there's toothpaste and concrete mix. This is hair gel. This is what we're going to be actually taking data from. So hair gel is really easy because you put it there, it's a clump, and you put your hand and try to do just a tiny bit, it's going to not budge. You say, come back, right? To go past the threshold, and then it'll shear, and there'll be enough stress on it, it'll become a liquid. And if you let it just sit for a while, it'll become clumpy again, right? That's what's in the bottle. So they're basically solid-like until stressed past the so-called yield stress point. It's a threshold. So the correct material characterization will bring understanding to unsteady processes found in the oil, food, cosmetic, and biomedical industries. So biomedical industries, it really need to understand this. I don't follow the thing, but it has something to do with delivery of particular medicines in certain forms, because our blood itself has some kind of properties like this. Measurements. This is his lab, Theo's lab. I was there, and this is when I started really coming up with a model, because it was fun to actually watch it. And this instrumentation is amazing. I don't know if I'll have the energy to go there. You can measure so much. And this is, with lasers and like full detail glass beads floating, and okay, we're not going there, but that's what Theo is doing. But this is like the hair gel on the microrheometer sitting there like a blob, and then this little disc can come and gently touch it. And then once it nicely touches it and becomes perfectly flat, you can clean it out, so it'll be a nice little film, okay, as thin as you like. And then you start applying torque. And then you measure how the thing reacts as well. This is some fancy machine. So it can, it's a stress strain controlled measure thingy. So it's a microrheometer. And so, then we can actually see how much stress is going to, make it sort of come back to solid, and what threshold should I cross to turn it into a liquid. So that can be measured directly. And this is the microrheometer, quite far away. So this is Theo. I think he was trained at the Weizmann Institute. He's a really clever guy, because I had a really horrible physics teacher in India, and so I studied only biology and maths. He really can explain physics to me in a very simple way. Miguel, he's the one. So he publishes in the Journal of Non-Newtonian Fluid Mechanics pretty much all his papers. And and he looks at these things in a different way. Right, so that's the roles we're playing in this project. So we need some kind of a richer model than the one that at least these guys sort of said is not good to use in this community, like 2009. And I'm only giving you the simplest version of it. There are lots of overlayers on Carroll law, all sorts of non-Newtonian complications that can be added, but they're fundamentally phenomenological in the sense that they try to mimic these xy coordinates, where x is applied stress versus experience strain. By experience, I mean I'm talking about the material's perspective, experiencing it. So it's a deformation rate. You can think of it, the material. So what's going on here downstairs is I'm increasing my stress, and I'm looking at the y-axis here, how it's deforming, and it's sort of remaining a solid basically, and then at some point it goes up. This is a hockey stick model, what they call the Bingham model. So Bingham actually founded the rheology world. He's sort of this Christian guy that's really went to Lafayette College, and I don't know, it's an interesting story. Like he quotes the Bible for inspiration and stuff, because everything flows at the right time scale. Deborah is the prophet in some subset of the Bible. It's a Deborah number.
Oh yes, I've heard of the Deborah number.
Yeah, I didn't put those slides here, okay, because I want to get into my world. So it's interesting. So because why this model is not good is because of the data they have from the microrheometer. Right? It's going to be very difficult to understand this scale. This is Theo and this world way of plotting it. It's an absolute reflected log scale plot. I don't know why they do this, but basically, it's showing that the point at which I go from a solid to a liquid as I increase stress is not the same point where I will actually come from a liquid back to a solid. Right? That's the hysteretic. So then they have this better model, which is the thick black line that they call the poor man model or something. And the motivation for that poor man model is essentially this. And this is the same motivation for our model. So what's the microscopic insight here? Viscosity depends on microstructure. That's interesting. That's gone. So yeah, viscosity depends on microstructure. So think of this, the log viscosity here and log shear rate here. So, think of these as little clumps of particles. You're going to have clusters of aggregates out here and really little ones out here spread out, right? You've got some kind of a, that's sort of the picture under the hood, and these are sort of the justifications. So you consider the material as a concentrated dispersion of structural units. These units can form a loose association of particles that can be destroyed by shearing, but reestablishes itself on just standing. The driving force for microstructural change and flow is the result of the competition between breakdown due to flow stresses and buildup due to inflow collisions and some kind of Brownian motion, right? So these are like coalescent fragmentation processes of some sort for the probabilist in the audience. To describe the complex behavior of the microstructure, one can introduce a structural variable into the model and let rheological parameters depend on it. This is what I call a phenomenological approach, or they call it a phenomenological approach. And this, so it's kind of beautiful. ODE, I don't try to understand this right now. It takes a while. But they're playing with arithmetical expressions and some nice standard functions to come up with vector fields that produce this picture. So I want to do this polynomials from neighborhood interactions. So when Theo came to New Zealand in 2012, he sort of told me this stuff, and we started working slowly on it. So this phenomenological model is not thermodynamically valid, and that was his concern as an experimental physicist. So the task was to make a simple thermodynamically valid model with observed macroscopic behaviors from microscopic structural considerations.
In what sense was that model not thermodynamically valid?
it didn't satisfy, the basic thermodynamic conditions, right? If you turn on the field free, and you'll see that in like third, fourth slide. It's basic statistical physics. State space. So this is our world now. This is the correlated site percolation. Let G be a regular graph. So it's just a two-dimensional square toroidal lattice. If there's anything unclear, please ask anytime. So map BBS sub n is the set of integers from 0 to n minus 1 squared. That's what I'm using to index when n equals 5 in that picture. So we call them nodes or sites. E sub n is a subset of Sn squared, the set of edges between neighboring pairs of sites. So of course E sub n is a subset of Sn squared because only neighbors matter here. As n goes to infinity, we study system behavior. Okay, we want to study macroscopic system behavior, like solid becoming fluid and things like that, on the sort of boundary-free self-dual limiting square lattice. I'll explain what those words mean. Boundary-free because we made it a torus. We don't want to worry about boundary conditions and stuff. And it's self-dual because you put a dot in here and then you connect it up. The dual graph is also a square lattice, so it's a self-dual lattice. So it has some kind of symmetry inbuilt into the geometry. So for example, a hexagonal lattice is not anymore. Right? So if it's hexagons, then you put dots around them, right? Is that right? You get a triangular one, right? Just making sure. I don't know what people know because I was talking to some kids at some of you at lunch today. So there's a huge mixed background. So we don't need to get to the end of the talk, but just because I don't want swear words. If anything is not clear, just ask. Okay. So each site S represents a microscopic clumps of particles. This is our state space interpretation. So that's S. Each edge, SR, represents a potential bond between neighboring clumps, sites S and R. Capital N sub S is just the set of all neighbors of S, the blue guys. That's just Euclidean non-modulo n. So it's a toroidal. So X of S in capital lambda is our set of faces, is 0 or 1. And this denotes the face of the clump at site S. Okay? So this is called the face of the site S. And what do we interpret this? So the site face X of S equals 0 corresponds to being yielded or ungelled. Okay, so it's some kind of liquidy now, right? So X of S equals 0 means it's like those it's yielded, okay, under your action. It's become tiny little particles now because we're now looking at clumps, right? And site face X of S equals 1 corresponds to being unyielded or gelled. So now y of SR is 1 if R is in the neighborhood, right? And it's 0 if R is in the neighborhood and the product of the site faces is 0. So only when two adjacent site faces, two neighboring site faces are 1 will the bond face be 1. So we are getting faces of edges from the faces of sites. So this is a interesting map. This is the reason why site percolation is still an open problem. I think was it Keston who solved the percolation constant for bond percolation, which is a simpler beast. But for site percolation, there's even basic open problems in probability theory. So y of S comma R is in 0, 1, denotes the face of the edge. And so we the interpretation is this. 1 means there exists a bond between sites S and R. Okay, so
let me just make sure I get the basic thing. If I have two clumps that are considered as gelled, the edge between them is considered gelled.
Well, okay, it's bonded.
Bonded.
It's important to distinguish between gelled fractions and bonded fractions.
Okay.
That's the whole,
So two gelled sites get bonded.
Yes, that's correct.
But otherwise not. Is that the statement?
That's right. Even if one site is going to be...
If one is gelled and the other is liquidy.
Yes, right, like right here. You see?
Then it's not bonded.
Then this is not bonded.
Okay.
But the beauty is this. The beauty is, as soon as I know this site is 0, I know that all these are 0. This is the information asymmetry from the arithmetic geometry of the lattice, right? So that's what I mean there. So you don't need to know who their neighbors are. You know the edges of this.
Even because you cannot be bonded to liquidy stuff.
No, because 0 times anything is 0.
Yeah, but physically.
Oh,
I
yeah.
think what he said is right?
Yeah.
You can't get bonded to liquidy stuff.
Okay, that's exactly the intuition, right? Yeah.
Yeah.
Sorry, I don't know how far into So anyway, this is the other point. If this is 1, then you really need to know what the neighbor was to know whether this is 0 or 1. That's the whole.
It's nice. It's a nice model. This is a model you're inventing. This is not a standard model, or this is.
No, I don't know exactly. I mean, it's just from Bramov's. He's the guy who can answer the question.
Okay.
I try to read all of Liggett's
interacting
interacting particle systems and cite it.
If you replace 0 by -1, it's the Ising model. Right?
Yeah, that's right. The Ising model has, as he pointed out.
It's similar, but.
Which 0 are you replacing? The 0 is not.
No, this is the ferromagnetic spins of the Ising model, where every site is now +1 or -1, or spin up or spin down.
Yes.
But there, as long as you're the same kind of spin ups, then you count. It's like a two-way. -1 times -1 is 1. 1 times 1 is 1. So if the -1s are together, they like to go toward -1, right? But here zeros are kind of like they don't care. It's like,
This looks more like not. There's things called kinetically constrained models that people like to study to understand glasses. They take spin-like models and assign dynamical rules. So I think this is an example of dynamical.
yeah, I'm definitely not claiming this is my invention or anything, right? I want to get to the ordinary differential equation using a quartic polynomial by actually expanding up to 3 orders around this, okay, on neighborhood configurations. Okay, so that's the story. So every site configuration X, okay, is in the space of site configurations, which is lambda to the power of Sn, which means all binary numbers mapped onto the lattice. So this has an associated edge configuration Y. The first note is Y of X is neither injective nor surjective. So it's not 1-to-1 or onto. Phases are in lambda over the toroidal square lattice. This is very different from the Ising model. And this is the arithmetical geometric site edge information asymmetry.
Quick question: can you have 2 gelled clusters, but they are not bonded?
No, you can't.
Why? If they're both gelled, they have to be bonded?
Yeah.
Yeah,
That's
exactly.
what the rule was.
That's the rule. Sorry, that's the rule. Yeah, exactly. Because 1 times 1 is 1 in the middle, right? The edge gets its meaning from the neighboring sites. So these guys are like, they're actually bonded. I don't want to go into English, right? But yeah, that's exactly right. That's just how it's defined, right?
It bothers you physically or something?
I thought I can imagine 2 clumps that are solid, but they're not bonded. Right? So
but it's not. I'm not calling it solid, right? So I'm calling it
Gelled.
Gellable. I don't know. Did a preprint. It's not.
You could imagine. The 2 gel things have some interaction with each other that forces them to bond.
Yeah.
Let's take that approximation.
Yeah. It's just that blue picture I showed you, right? That's what they believe anyway. That's how the ODE, phenomenological ODE, comes from the same insight. So it's not anything I'm making up. So the arithmetical geometric site edge information asymmetry is just because of this multiplication with zeros and ones as opposed to -1s and +1s. So what we will be doing is an ODE approximation to the expected quantity A over bar. So what is A over bar? This is a random quantity. It's simply the gelled fraction. So I count all the ones in the sites and divide by the total number of sites. Okay, so that's a fundamental quantity of interest to these guys. Okay, so pi of x is the probability of site configuration x. Okay. So this is just 400 level statistical physics, so I'll just step through the ideas very carefully. So you have this form, the probability pi of a site configuration x. So now lowercase x is the 0, 1 map to the whole lattice. Is 1 over this constant times e to the blah blah. So what are these things? Script e of x is the energy of a site configuration x. Lowercase k is the Boltzmann constant, and capital T is the thermal temperature. And z sub kt is the normalizing constant or the partition function. By x sigma, or distributed according to pi, what we mean is that the random site configuration, uppercase x, has probability distribution pi. Okay? That is, the probability of the random site configuration taking a realization, lowercase x, is simply given by pi of x if x is an allowed configuration and 0 otherwise. That's how we move from the energy to the distribution.
How do you define, what is the energy function?
That's what I'm about to define. I just said there is some energy. I haven't told you what it is, but I need to say that there is energy, and then I'll go to distribution. And then I'll tell you what exactly the energy is for this model. So before I define what exactly the energy is, we first note that pi is actually a so-called Gibbs distribution. Why is it a Gibbs distribution? This is because our neighborhoods, n sub s, have only 2 clique types. So what's a clique? Clique is essentially some kind of a structural equivalence of subgraphs of some graph. In this case, you only have 2 types of cliques. You have sites, and then you have bonds. You know, I'm talking about this square lattice. There are only 2 types of cliques. Okay. This is all this language from this world. So given parameters alpha and beta. So what we're going to say that alpha and beta are our materials' rheological parameters. They're going to measure something energetically locally. Okay. So where alpha is going to be greater than or equal to 0, any real number, this is going to be called the site-specific threshold. Beta is any real number, and this is called the interaction constant of neighboring sites. And parameter sigma greater than or equal to 0 for the externally applied stress. Okay? So we have an external stress, and then we have 2 rheological parameters. So it's a tri-parametric family. Therefore, the Gibbs potential over the singleton clique, just a site, is this. This is the potential of a site of a configuration. It's just given by this relationship. So I'm defining it, sigma minus alpha times xs. 0 if xs is 0, it's sigma minus alpha if xs is 1. Okay? So when I have, sigma, the applied stress has to somehow fight with the site-specific threshold. And then the beta, the interaction constant, it has to fight based on whether the 2 things are bonded. That's the idea. Okay. So those are just the potentials. So the energy function of this potential is the following. So you get the energy from the potential by summing over all cliques. Summing the potential over all cliques, you get the energy. So of course, we have to sum over all cliques. So this is just the singleton cliques, which means we have to sum over the whole set of sites for every site. And then we have to sum over all the edges for every edge, because only 2 kinds of cliques. The potentials can be summed, because we've defined them in the previous slide. Now I just do this, because that's what I call those 2 things. Okay, so if you look at that already in physics, that should tell you it's transporting this intuition now. So E of x only depends on beta and the difference sigma minus alpha. Something to note, because we sometimes go back to this simpler parameterization. We can reparameterize by sigma tilde. So sigma tilde is going to be sigma minus alpha. That's going to be greater than or equal to minus alpha. So for a fixed alpha, we can sort of absorb it to sigma tilde. And now the energy is just given by this expression, that's all. All right. So the thermodynamic validity by Gibbs construction is the following. This is all standard stuff again. The idea is simple. So let the expectation of a function g with respect to distribution pi be bold E of g. That the internal energy of the system is script u. This is just the expectation of the energy. And then the free energy of the system is script f, and it's minus Boltzmann constant times thermal temperature times the natural logarithm of the partition function. Our model satisfies the standard thermodynamic equality by the Hammersley-Clifford representation theorem. This is standard stuff, right? Well, anyway, this isn't...
This seems like a lot of fancy technicalities.
Okay, it doesn't matter. Forget about all that, but that's how Bremont's book explains it.
Okay.
And
nobody here understands it except for experts.
okay,
Isn't
fine.
that fair to say?
Okay,
Yeah.
basically, by construction, it satisfies. Well, anyway, Theo was all psyched about it, and I said I did the construction this way because I knew it would actually satisfy the thing. So it doesn't.
Now it's a thermodynamically valid model. So you're now going to tell us what it does.
Okay, we sometimes emphasize this dependence. That's all, right? So by alpha, beta, and sigma. So this is called the local specification, pi sub s from local energy. The local energy at a site S of configuration X is the following. So basically, you sum over all clicks that contain S, the potential, and that's the local potential. You can just go directly here, and this basically says the local energy is just the phase of site S multiplied by sigma tilde minus beta I.
Right.
And what is I? I is our basic variable now of interest. I is the number of neighboring sites of S that are in phase 1. So then the local specification is pi sub s of x. And the local specification is what we need to run the Gibbs sampler, the simulation algorithm. So pi sub s of x is e to the minus 1 over kt, blah, blah. What is this saying? This is saying I only need to know the probability of my current state at S, and then I have to look at the only 2 other places I can be, right? So that's all this is saying. And so this sort of, says that, because I only can, if I'm at 0, I can only go to 0, or say come back to 0, or go to 1. And so I can just do these ratios and figure out how to move in this Gibbs way, which is purely locally. And this theta is essentially this quantity. So this plays a fundamental role in the local transition probabilities. So that's the main thing. So then the local specification is all of that. Okay, this is all standard stuff once you have the potentials defined for your model. So in this work, we focus on the effect of varying external stress sigma at a constant ambient temperature. So that's what these guys want to do in the lab. And therefore, without laws of generality, we take kt equals 1 and work with pi of x directly.
Just a quick question.
Yes.
So, is another way of summarizing what you said that you got around the enormity of computing the partition function by making this local
exactly.
observation? Okay.
That's right. That's the whole idea of a Gibbs sampler.
That's
right.
cool. Yeah.
I'm confused, but would this be true if the partition function, if your energy wasn't quadratic? Your energy is quadratic, right?
Energy is quadratic.
It's because of x times x in the bond term.
Right.
So it's quadratic, you can compute the full partition function.
I mean, I really don't know a lot of physics. I just read this book, and he used to ask that guy. That guy is the actual probabilist who talks to physicists, right?
His energy function is a natural one, right?
Yeah.
Having this property makes it already worth studying from your math point of view.
Oh, that's good. Thanks. Try to get my heart beating slow. I didn't sleep last night. It's full moon, and I hate making my first talk. This is my first talk of this work. I just was preprint a couple weeks ago. So anyway, yes, as you pointed out, you can see this whole thing as a Markov chain on configuration space directly, right? And it's just basically saying my model is just the xn, the xn valued Markov chain, capital X of m, right? Where m is this discrete time with initial distribution with the direct mass at x0. Then the m step transition probability is simply given by this, right? So and you need the 1-step transition probability to take its mth power, and that's just this. This is exactly. So basically what this is saying is, the blue stuff is the self transitions, and the red stuff is the non-self at S transitions. And theta is actually a function of 4 objects: the site you're at, alpha, beta, and sigma. Of course, I is also encoded, right? So that's basically the idea. So it's a Markov chain. So that's how we're going to do the ODE approximations, by looking at this Markov chain and its projections. So in English, XFM evolves by these locally specified rules. So the so-called Glauber dynamics of the Gibbs sampler is the following. Given a current configuration X, we choose one of the n-square sites in Sn uniformly at random, denote this chosen site by S, and then let the number of bondable neighbors of S be I. It could be 0, 1, 2, 3, or 4. And then finally change the phase at S to 1. That is, set X of S equals 1 with probability P sub I. So P sub I just encodes how many neighbors are there around it in phase 1. And this is basically it. And then you keep going. And let's look at this function P sub I graphically to get more intuition. P sub I is the probability that the site S with I neighbors in phase 1 is also in phase 1. So here are P sub I's for different values of alpha and beta. So let's look at this. So actually, let's start with this one. When beta is 0, it's easy because it doesn't matter. All of them are the same, right? Because I times beta becomes 0, right? So that's nice. And then you have these other things. So if beta is positive, let's say beta is positive, then you see these dotted things go up, which basically means P sub 0 for all sigma, okay, lies below P sub 4. And then it flips the other way if beta is negative. Right? So there's this, beta plays this role of what I will call, so the other thing important to note is alpha does a translation. It's a translating parameter, and beta controls the distance between the P sub i's. Right? So this is why we can justify sigma tilde equals sigma minus alpha pictorially as well.
Should those betas, like in the axis labels, like be minus 1 for should?
So this is minus 1 and this is minus 1. This is 0 and 0.
Okay.
This is 1 and 1. This is 2 and 2. And all the alphas are 8 here, and all the alphas are 0.4 here. So this whole thing moves here.
Okay.
You're just not seeing this because it's below the values sigma can take. Stress is positive. See, if I just translate this, it just moves with alpha. And sigma just is just the x-axis, right? And beta is the one that flips these guys. The sign changes, it flips all of them.
Sorry, can you remind us about alpha and beta physically?
Yeah, so alpha
I
is
remember
the
what alpha is.
Yeah, it's the site-specific threshold.
Right. So it's not, after I start stressing, if I stress by more than alpha, I tend to get liquidy. Isn't that right?
No.
No.
So sigma is how you measure how much you're stressing it.
Yeah.
So
that's sigma. Yeah.
Yeah.
And
So
then what's alpha?
I mean, alpha basically is the site-specific threshold, right? So it's saying that if alpha is very high, then I need to fight it linearly. I mean, because there was a sigma minus alpha interaction, right?
Yeah.
So it's a.
It's how much it wants to be gelled. Each site wants to be.
Each site wants to be gelled.
No, it's a matter of whether it's bondable with its neighbors or not.
Yeah.
I actually read through the entire IUPAC nomenclature in the preprint, literally and then they have all these different words that these people use.
But the beta is the thing that controls how much one site cares about the state of the neighbor.
That's correct.
Right?
Yes.
So, I mean, I'm trying to think like in Ising model terms.
Beta is
One of them is sort of like J.
Right.
The beta is kind of like J, right? Beta is the thing that controls
Yes.
the site-to-site interaction.
That's right.
And alpha is the thing that controls what I'm trying to understand. I don't quite get what alpha is.
It's okay. The other way to think about this is
It feels like it's a local field, some measure of something about a local field, but I don't understand. quite
I mean,
what.
it's what's encoding the information in the site itself.
Right.
It's just like a
But what?
So
it's like how much sigma do you have to put on before?
Exactly.
Before what though?
Yeah.
Before.
Well, actually, you know what? You'll totally understand this in a second. Because when beta is 0, okay, I re-understood it now. So when beta is 0, right?
Yeah.
This model is exactly the site percolation model.
Yes.
Classical site percolation model. What does that mean? But that's a different intuition, right? Different interpretation. So it says that I don't want to go into subgraphs of percolation.
Well, because that's what the correlated is about, right? The fact that you have a beta is what makes it correlated, I think.
Yeah, that's correct. That's right.
Without the beta, it's just ordinary site percolation.
Yeah, so maybe we should, this is the slide. Sorry. So when beta is 0, you have a non-interactive model.
Right.
So this is classical site percolation, like I said.
Yeah.
Because now all the P's are the same. Okay? And the model, because it has only 2 parameters, this is what the interpretation is. 1 over 1 plus e to the sigma minus alpha is the site percolation probability P. This is exactly a recoding of P. And when beta is greater than 0, then we have this relationship. P0 is less than P1, less than P2, and so on. Right? And when this is called agglomerated interactions, and I really carefully define this through the nomenclature in IUPAC. And then this is anti-agglomerative interactions. So this is sort of English. So if beta is less than 0, the probability of a site being in phase 1 decreases with the number of its neighboring sites also being in phase 1.
Right.
This is what I should have probably.
No, this is clear. This is good. So it's just so beta tells you if your neighbors are already gelled, do you want to be gelled?
Yeah.
And if beta is positive, it does. You do want to.
Yeah.
Otherwise you want to avoid it.
Yeah. Right.
Right.
So there are 3 pictures later in a few minutes, right? But there's you'll see the patterns.
But I'll just keep quiet.
So that was the time homogeneous Markov chain. But what Theo really wants is a time inhomogeneous Markov chain because he wants to change the stress sigma as a function of time.
Yes.
And typically, this is what they're interested in: stress ramps. Stress ramps are fundamental for oil processes as well. So, sigma. If sigma varies as a function of time blocks of length h under bar, defined as h times n squared, and given by the function sigma of m, so that's what's given here, for each time block m. That means for each time block, I'm spending that much time, okay, in it. So these are actually tiny little intervals, the step functions. So then we have this time inhomogeneous Markov chain, x of k, where k goes from 0 to m, h under bar, with the transition probability matrix at time k given by P of k. So P of k is simply a tri-parametric family of these transition structures because sigma is changing for each block. You see, because sigma is now indexed by the time block. So then the k-step configuration probability of k less than m h under bar is just the probability given by taking the initial condition and then raising it to the block length power while changing the sigma of m. This is just standard inhomogeneous Markov chain stuff. There's some boundary conditions you have to worry about if the time you're looking at is outside the block and all that, but it's okay. So now we're done, right? We have our stochastic model almost done, but we have to ask the most important question: what are the sufficient statistics of the site configuration? Do I need to know everything about this crazy pattern, or something much more simple? And that's just the 2 things you only need to know: is the gelled fraction, which is the fraction of gelled sites, and this is bonded fraction of connected pairs of neighboring sites. This is A over bar and D over bar of a configuration X. Okay. This is 2n squared because there are 2n square edges in an n squared lattice. So then the energy of a configuration X is simply re-expressible in terms of A over bar of X and B over bar of X this way. So we don't need to know the full picture, we just need to count these thingies. So that's so picture time. Sorry, this is like Nussbaum's training. I can't do the pictures before I do the definition, slides. But so these chains are our correlated site percolation model. So we can try to see sample paths of time homogeneous chains via the Gibbs sampler now, and then we'll see a movie if time permits. Am I already done with time?
No, you're fine.
Oh.
You have 15 minutes.
Okay, 15 minutes. Okay, maybe I should go to the movies or the pictures. So let's just look at this. Oh, this is interesting. Oh, it's not all messed up. So this is basically the phase transition without stress, right? So the world of site classical site percolation is just living on this line here. Why? Because beta is 0. It's classical site percolation, no interaction. And then just this line. So now just imagine that there's this hueing here, the shading, and then there are these circles that are covered by black dots. And I'll explain what they are in a minute. And note this blue line. This blue line is sort of a non-rigorous estimate, up to an interval of the threshold exactly at which the so-called percolation cluster forms. This is the phenomenal phase transition of interest when there is no stress. So if you let something sit, will it form a percolation cluster? What's a percolation cluster? It just means there is a connection, there is a whole bunch of connected edges going all the way from the bottom of the lattice to the top of the lattice. Right? The biggest cluster in there, cluster means connected things, goes from top to bottom. That's a percolation cluster. So that only forms if alpha is bigger than that number, because that's exactly where P should be what for site percolation, some number inside 0, 1. Okay.
So a black dot means that you don't have a large
here's the let me do the English directly like I've written it. So the shading of the circles at each alpha beta indicates this, whatever this thingy is. What is this? This is the proportion of the lattice occupied by the largest cluster of gel sites at rescale time t after having initialized from the all fluid configuration. Parameter values that do not lead to a percolation cluster, which is this vertically spanning largest cluster, after each one of the n squared equals 10 to the 4 sites has gone 100 transitions on average. So this is kind of as close as I can get by killing our machines for 2 months, in New Zealand. So it was just super paranoid. But it's just a realization. I'm not estimating these things perfectly by doing multiple Monte Carlo simulations for each piece. That's not the point. But there are some interesting things that are happening. This is in the log scale for alpha and beta. So now, what's with the black circles, black edge circles? They are the ones highlighted like this. So, so this means the percolation cluster doesn't form.
Right.
And the way it goes is something like that. Okay, this is just the phase transition without stress.
So alpha bigger than 0 means a site has a propensity to be gelled.
Yeah, sure. Yeah, that's a good way to
more
put
than
it.
to be liquid.
Yes. Yeah, it's like bondable. It's ready to bond. It's like ready to love. Otherwise, it's like, oh, I can't do it. Something like that. Okay, phase transition with constant time asymptotic stress. So now what I'm doing is I take a constant non-zero sigma, and then I let time go to infinity. And then for each alpha beta, I look at what's happening to its quantity. Now I'm not interested in percolation clusters, but I'm interested in the solid to fluid phase transition. Right? Because this for each parameter value, I have this thing I'm running right on the configuration space. So I'm now going to initialize with all 1 state and all 0 state. That's how I go from. So if I initialize with all 1s, this is the picture I get. Okay. And if I initialize with all 0s, this is the picture I get. And the picture basically is 1 means everything is gelled, so you basically have solids here, right? And liquids on the other side. And then what is this picture? This is the hysteretic difference of these two. So this is basically your, where the hysteresis region should happen. Okay, this is all done by simulation. Then the value of A over bar is the gel fraction at rescale time t. I think I said all this. So now here is our biparametric quartic ordinary differential equation for approximating the bold A over bar of t. The bold A over bar of t is the expectation for a fixed sigma tilde, right? Which is sigma minus alpha, and a fixed beta, okay, of the random gel fraction, okay, and so that's just the gel fraction. The expected gel fraction can be approximated. This is the phase portrait of it. So what you're looking at is sigma tilde and beta down here, and then this is just the bold A over bar star is the fixed point. So you're just looking at the mapping of the set of fixed points for each alpha beta, and you can see this basic thing like that. So now this is the ODE. So it's a okay. So it's a quartic with these p's. Remember the p functions, because alphas and betas and sigmas are all sucked into the p's. Okay. So I think it was like 3 pages of derivation and detail of the definition and everything, if you're interested. But so here's the last point is, if you compare the black triangle from this ODE, which is projected down to this yellow triangle, that should match somehow, right? And so let's watch a movie.
A bar is the fraction of the gelled size, right?
Yeah. So I hope Gutenheimer can help me with the right perturbation. So what we're going to do is just increase stress on this ramp and watch this movie. So this is time in homogeneous Markov chain. So stress is increasing slowly. Everything is gelled, and you have to fight hard because I set alpha to 8. Okay. So, but also I sort of did this old movie, so I changed the Boltzmann constant to 0.156. It has to be positive for the whole thing to work without positive generality. But so now you see little holes are being punched in, and then if you observe carefully, this goes down smoothly and comes back, and I don't know. This will basically go here and stay here, which means everything is fluid now. Black, everything is just 0. So I'm not going to, so we'll fast forward the movie a little bit. And then if you go back here, a little bit further, it's coming back. Now let's watch this. So this is going to just go, see, this is just going right back through itself because beta is 0. Okay. So the next movie is beta is greater than 0. It's on the same stress ramp. So now you're going to have to increase the stress to some level, and maybe I'll speed it up. Okay, see, it's red, but it's going to start, and see the way it clumps up when it breaks. And so let's speed up the movie a little more. Guys, come back, go faster. Okay, so then this is going to now have the hysteresis. This is the whole point. You know how the amount of money you can make by making sure that the amount of shear in the oil wells is actually not as high as you think, but still not get gelled, right? See, that's sort of the commercial. And then it just goes up like that. Okay, so here's the cowhide picture. This is probably what I should have shown in the beginning. But these are for values of, now we're looking at the exact solid fluid interface when the thing is exactly at 0.5. When beta is positive, we get this sort of cowhide-like pattern because things like a clump. This is like a preferential attachment world. And then this is beta equals 0, so it's pretty random. And then here's a checkerboard pattern. This is anti-agglomerative, agglomerative, and non-interactive. And this is sort of cowhide, random, and chessboard. So hysteresis in the gel fraction is this. So now I'm showing you a lot of stuff. The 1, 2, 3, 4, these are 5 Gibbs simulations of this curve. And the black line is actually the ODE approximation to it, the asymptotic one. And, so the green one is the actual ODE approximation. But then when I perturb it slightly by just a translation, I can get a good fit. But for beta equals 0, I don't need to do any perturbation at all. I can get a perfect fit with the ODE because I'm only using the A bar. Problem with the ODE is I'm not using B bar, which is a sufficient statistic. That's why I need to do this silly translations of the vector field without any real insights, right? So then this problem gets worse, basically. So that's the stress ramp again. And this problem gets worse now when beta gets larger. You see, here's my phase transition gets stronger in the simulation. That's the pink stuff. And then my ODE plugin estimate will be just this. It'll be so far away. But then if I move the triangle just right, by just translation, I can fit it in. Just kind of did it interactively. So there's something going on, and someone who told me something about singular perturbation theory, singular geometric perturbation theory or something, then that'll be a nice way to proceed to make this precise. So here are some concluding remarks. Using an interacting particle system model, we can fit data better. Each material can be empirically identified by its rheological parameter alpha. Oops, used a slash. Sigma tilde for science or engineering applications. It would be nice to use geometric perturbation theoretic ideas to better approximate the expected gel fraction. Ideally, find a large enough neighborhood, much larger than just what I call the binomial neighborhood of configuration approximation. That's how I bring these polynomials out from this approximation, right? So that you can contain a 2-parameter family of ODEs in terms of not just the gel fractions, but also the bonded fractions. That's what's missing in my information. So I need like a two-dimensional ODE. Anyway. See, there's a lot more done in the preprint, but using interval analysis and stuff to make sure that the computations are right and ODE calculations. But anyway, time kills. Many thanks to Steve for the integrative graduate education research traineeship, where graduate students are paid for 2 years to not TA and take courses in any field, as far as I was concerned. That was really fun. The UC College of Engineering gave me a sabbatical grant to come here. I'm actually visiting Michael Nussbaum to get tutorials in the 2nd and 3rd week of November on quantum mathematical statistics. I'd really like to know what's going on there. Thank you very much for your attention. If you want the preprint, I don't put it in the archive. It's on my webpage, and these guys are trying to parse this into publication.
Thank you very much. Some more questions?
Sorry, did I exhaust you guys?
No. Am I right in thinking that there was the reduction to the ODE that's the few pages that you weren't showing us? That is, there were various P's and stuff. I mean, I just saw an ODE at some point.
Yeah. You want to see that and get the whole thing out of it?
Not necessarily.
That's possible. So actually,
but you said something at the end that was more specific than I heard during the talk, but maybe I missed it. You said something about you only looked out to a certain distance away from the site,
that's it.
And that's how you derived it.
I
So
mean,
is it a mean field approximation?
I don't know.
Within that small?
That might be. I actually don't know.
Going out farther will bring in that other variable, the B.
Yeah, I mean, I don't know. It could be. I don't even call it mean field or not. I just call it OD approximation.
It seems like it kind of is.
Yeah, he would know.
I don't know.
He hasn't read the paper though.
That's what it looks like.
Yeah, it's all sure.
Where does the time scale?
Oh, that's the most important thing. So I'm actually I'm doing a very subtle simultaneous spatio-temporal rescaling for the thing to work. So the time blocks and all of these things, there's a way to do the rescaling right, and it's not that complicated, but it's something I had to think about a little bit. So there's a time-space rescaling, right? I mean, actually, to tell you the truth, this, my older daughter Anusha helped me with this neighborhood configuration calculation, because I need someone to co-articulate, and she's getting older and not interested in doing maths for fun. It's just you have to make this huge Hesse diagram of neighborhood transitions, and you'll see these binomial calculations for the approximation. It's just literally like playing with like an 8-year-old. So that's how the intuition came, right? But it's very difficult to do it by myself sometimes, right? Talk to somebody.
I have just a suggestion for think about in this model, which is, instead of doing this complicated thing where you kind of gradually ramp up the stress, you could ask a simpler set of questions, which is just understand the stationary distributions of these chains. So what the Gibbs measure itself, and in particular there will be a range of stress parameters where you have two potential wells, like one centered at the all zeros and one centered at the all ones. And you should be able to get a handle on hysteresis by understanding, like, suppose you're at the all zero well. Well, if you run your chain for long enough, you'll have this nucleation event where you have a big enough cluster of ones that forms that it takes over. And it puts you into the other well.
Yeah.
And for the easing model, this stuff is understood, and you can probably adapt a lot of their machinery.
And I'm not a probabilist. I'm in a department with constructive mathematicians and biomathematicians. I have to publish in these fields to get promoted for the next 8 years. 'Cause, in New Zealand, your money increases according to how you get local respect. After that, maybe. But that's a great idea, and that's a. I'm not trained in proper probability because although Derived was my advisor, he let me do my own thing, which is nice of him, but also it limits me to do more clever probability. But we can talk more. I'll be here for another 58 days.
58. Okay. Sounds like a while.
Well, do we have any other questions, or should we go get some cookies? All right, let's talk in the room next door.